KNN is k nearest neighbors, which is experiment 3, and after that, naive Bayes, which is experiments 7. And if time permits, we'll also cover experiment 9, which is into words classification. So without further ado, let's start with KNN, K nearest neighbors, as we know it. So let me give you a little bit of brief what KNN is. Let's say there's a student goes to school and there are three sections full of students, and they have to decide, the teachers have to decide, we have to put the student in which class. So that decision actually will be based on some parameters. Let's say the marks, okay, or the sports uh, quotient that the students have scored. It can be anything. So that is just a given what would be the the deciding point. So that whatever distance is less, whatever he's close to whatever class, he will be given the same class. Same way, in a two-dimensional space, we give a point, and that point decide that the distance of that point from the neighbors decide what class it will belong to. So let's say this is the category A and this is the category B, and there's a new data point which comes here, and this KNN will help decide which category it should belong to. So now we can see that it is more closer to category A than category B. So after the this KNN algorithm, it has been decided that the new data point will belong to category A. Without any further ado, let's start our code. So these are the libraries that we are going to start. We are going to include this. We are going to import these libraries. So NumPy, we have already discussed why we use this train test split. And this A neighbors classifier, this is the classifier. This is actually the class that is responsible for training the data. Training actually, in this, we are not training. This is called a lazy algorithm because we are in training in dot fit method. We are actually storing the data points, means the category A and the category D. And then when we are going to predict it, we are just going to calculate the distance between the new data point and the already presented data points. We will dive into this. All right. So after we have actually imported these libraries, what we'll do, we'll prepare the data. So right now, in your lab, it was written to assume the data set. So I have taken three classes here, not two. So now we have three classes with 100 data points, each as a sample. Okay. So this is where we create the data. We decide how many data points, and then we create the data. So this we are using dot random normal to create the data. This will be the starting point. Let's say 2, 2, 5, 5, and 8, 8. These are the mean points actually, and we are creating the whole data. Let's, as you can see in the picture, we are creating the whole data. Let's say if this is the minimum point, see my cursor. So if this is a minimum point, mean point, sorry, and so this is the category that has been created. If this is the mean point, this is the category that has been created. All right. So this is how we are going to create three categories. All right. So now what we're going to do is we are going to concatenate the data and the labels. So you can see that data, and also we have labels. What are labels here? So The labels are nothing, just in this data, we are saying that, okay, it is category A and this is category B. So we are labeling as 0, 1, and 2, nothing else. Okay. Having label 0 to class 1, label 1 to class 2, and label 2 to class 3. All right. And here we are combining those data and the labels. Axis is equal to 0. It will always mean that the data will proceed, the whole function will proceed row wise. Here we are shuffling the data. Here we are shuffling the data. So it would get random. Okay, we'll get into this later. Let's go to web because we've already imported key neighbors classifier, so we don't need to define the whole thing. Okay, so what our key neighbors classifier does, it computes the distance. Let me see if that, yeah. So it computes the distance between 2 points with this formula. And we have also decided one more thing, that is k is equal to 6. Why we have taken k is equal to 6? We are going to compare with not all 100 members, but with 6 neighbors. Okay. So, okay, we are splitting the data here and we are giving a random state. And right now the test size is 0.2. That means 20% of the data will be used for testing and the 80% of the data will be used for training. Now convert labels into integer type. Okay, that we don't need to do since we have already imported that. So we can comment this. This is the step where we are using this KNN. We are using this KNN to fit the data. Sorry, to this is right now. This right now we are actually calling this and making an object out. This is where we are fitting the data. KNN.fit. So in fit, let me show you what it does. Okay, so in fit, it does nothing but store the data. Okay, so it is storing all the data points. So in predict, now I've stored the data point. Now what happens in predict? So let me do this. So now it is showing accuracy 1.0. Let me get this size. So right now we are getting accuracy of 96%. And we are taking the test size of 30% and the training size of 70%. So this is a good accuracy. 1.0, it could be overfitting. That is why I'm actually avoiding. All right. So let's get into this. What is this predict and how we are actually doing it? So what is the step of k nearest neighbors? First, we select the number k in neighbors, how many neighbors we are going to decide. Then we calculate the Euclidean distance. Then we take the k nearest neighbors as per the calculated Euclidean distance. So you all know the theory. Okay, so you all read about what KNN and how KNN works. But let's get into the code and see how actually it is being implemented in Python. Okay, so this is the class K neighbors classifier. And if, let's say, I'm not importing this, not importing right now. So this class K neighbors classifier will be considered. First, let me show you how it is working. So it's giving me a very good accuracy, 98%, almost 99%, because we have a good data set, good amount of data with us. So that means this is an effective classifier that we have defined, and it is very much similar, or you can say it is exact what it should be. There would be some of the methods that is not being included in this. That would be there in K-numbers classifier, but it's not is not in whatever we have defined. Okay, but what the main thing is, that is the predict method. So right now it is taking an empty list. So okay, for empty list, why? Because we are going to store all the predicted values. For test point in K-test, let's say in X test we have 100 values. Okay, or 90 values, as it saying that we have X test of 90 values. All right. So because there are 300 data types, and sorry, there are 300 actually data points, 300, 100, and we are taking actually what we are taking 50% of the data for testing. So that is why it is 90 into 2. It is written because any data point will have a coordinate. All right. So for this, for test point in K-test, distances it is taken. So it is going to store the distance. For train point in self dot extreme. So now whatever is stored here will, so it is the training data basically. So that you can say, okay, it is the whole thing, whatever the training data, because it is all combined. Distance is equal to np dot is square root np dot sum test point minus train point is square. So basically this this is where equiradiant distance is being calculated. Okay. Now I'm going to append that distance. So for all this point, we are going to append these distances. Now we can see, okay, we have decided here that n neighbors will be 5. Okay. So not actually 6, I'm taking 6 here. Okay. So n neighbors, because we have taken 6, so n neighbors will be 6 now. So what it is doing? It is doing nothing, but it is first it is sorting the distance on, because now distance is a the whole thing. The distance is the and list which contains all the distances. The data from one data point, because this test point is one data point. It contains the distances of all the distances from all the data points. What we are going to do? Self dot n neighbors. That means 6. We are going to take the top 6 distance. Okay. Now, when we are going to take the top 6 distance, then in nearest indices, we'll know that what are the nearest indices. Now we'll see what are their nearest labels. Now when we are putting this self y train and we are putting the nearest indices in that, we will know, okay, what are the nearest indices. Sorry, what are the nearest labels are for these. Okay, now we'll predict label based on majority vote. So whatever will be the majority, it will say, okay, this is for this point, this is the majority. Let me show you the figures. So it will when it will calculate the distance, and it will sort what is the, let's say, 1 unit, 2 unit, 3 unit. So it will sort, okay, this is the majority vote, this is the minimum distance here, this is the minimum distance, and this is how this is the majority. According of this majority vote, we have decided that this data element belongs to category 1 or 2 or 3. Okay. This is after this whole prediction, we are going to append this to YPRED because this is a list. Okay. After this whole list is being populated, we are going to return this. So this is the whole story of K nearest neighbors. Okay, so I will explain to you not only not only the whole thing, the how this works in algorithm, but also how it is actually mathematically working inside the algorithm. So, are there any questions? There are no questions, then I'm going to proceed to the next topic, that is Naive Bayes. This is actually your lab 7. Yes, experiment 7, I guess. So, classifying the English text. So, and with KNN now, we are starting naive Bayes. So, why this naive Bayes is being used? So, let's say I'm saying that this is the first document, this document. I have a set of sentences and I'm categorizing those sentences into particular categories. Okay. So, in your experiment, I have got some some examples, but I have taken my own example so that I can get a good output. Because according to this, because this is very less of a data, and it was not actually amounting to anything. So accuracy was being shown 0 to 0. So even now I have a less accuracy, but even now I'm having a less accuracy. But because we can conclude we don't have a very large file, because if we take that large file, then to do the data cleaning and stuff. So right, when you are going to actually perform in this Navias to a bigger text, you'll have to do the data cleaning and stuff. Okay. And first you'll have to extract the sentences through the split and everything. Right? You already know that, I guess. So let me show you what actually the data that I have taken. I love to eat pizza. So now the label for that is food. I enjoy watching movies. Label for that is entertainment. Movies are great source of entertainment. So using these keywords or anything, okay. So using this statement, if I give this statement, the algo should be able to understand, okay, what category this statement belongs to. That is why I'm using this naive bias. Okay. So how will you actually do that? For us it is very very easy, because we are humans, and since we are born, we are being trained and fed a language which according to which, when I'm seeing this, movies are a great source of entertainment, or I enjoy watching movies. When I'm seeing this, I automatically say, okay, this belongs to entertainment, because in my mind movies belong to entertainment. Okay. So you can now I understand, because I have been trained since the beginning, since my birth. I have been trained in a language. Okay, but how the computer knows? Computer doesn't know anything. Okay, how this machine that I'm training knows? So for that, I'll have to break down those statements in vectors. We'll get into that. So right now we are importing three libraries. So counter vectorizer, train test split, and multinomial NVs. This multinomial NV is actually a NIMS which will actually train. But what about count vectorizer? That must be a query, right? So what is about the point vectorizer? So right now, what we're doing is, let me just run these. Just let's pick, uh, not going to run this. Don't need it. Now we are splitting the data into data train and test set. Right now, I've taken a bigger test size because I was having issue with accuracy. Okay. I've taken one random state. One random state means every time when it runs, the same program, it will take the same set of random numbers. I'm sorry, same set of random distribution. Now let's talk about the count vectorized. What is actually is. So suppose we have three uh, documents, or you can say three sentences. We want to convert these text documents into numerical representation because we know that computer understand numbers, right? Okay, so how are we going to do that? First of all, we're going to do the tokenization. Okay, so count vectorizer first breaks down each documents into smaller units called tokens. In this case, tokens are nothing but words. Okay, the cat sat on the mat. So all these words are tokens. After tokenization, we have a list of unique words, that is vocabulary, across all the documents. So I know that okay, we have the two times and cat one time, sat one time. Okay. After this, we will see what are the counting occurrences. For each document, count vectorizers counts how many times each word in the vocabulary appears. It creates a numerical representation for each document based on the count of these words. Okay. So consider this as a as a row and column. So these are the columns and these are the rows. Let's say. Okay. So in this statement, the cat sat on the mat. The has been appeared two times. Cat has been appeared one time, sat one time, and so on. And the whole thing after this. So these are the unique words. So let's say dog ate my homework and our friends. These are not present in this documents or say sentence. So I have given zero to this. Now the dog ate my homework. Same way, this will also be the frequency of this will be calculated. So now the appears two times. The dog ate not actually two times. We have only one time. It is a little bit of there's a little bit mistake in this. Sorry about that. So it will be one actually. So let me actually correct this. So the dog ate my homework. So the has appeared one time, and dog ate much this. Cat sat on mat. There is nothing, but dog ate my homework is there. So one, 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 one. Right. So you understood how we are doing the numerical representation. So now in this representation, each row represents a document. Okay, so that is just, so this is how we are actually converting our text into numbers. Now that converts into first into tokens and we are converting like this. So now we have a matrix. This is where we are initializing this, making this object of uh, count vectorizer, and we are naming it as vectorizer. You can name it anything, it's a variable. You're actually creating an object of that class. Yes. Okay, so now if we know that now we know that what we have to do with this vectorizer. Now this vectorizer will actually let me show you what is the use of this fit transform. So now that the correct usage of fit transform is to fit the counter vector account vectorizer on the training test data and then transform both the training and test data based on learned vocabulary from the training data. Okay, so now what it is going to do, it is actually training the text data and based on the whatever, because it has a particular set of vocabularies, it has unique words. All right. So we are going to assign some of the unique words to a particular label. That is what we are going to do. Okay. That is why now this what is this doing? Fit transform the command fits the count vectorizer on training text data and transform it into numerical feature vectors. That is what it is doing. Okay. Now This is the training data and this is the testing data. It learns the vocabulary from the training data and converts the text data into a matrix of words. That's what we have seen. Okay. So what I have done here is xtr is equal to vectorizer dot fit transform x train, xts is equal to vectorizer dot transform x test. Then I have printed both of them. Okay. So what are these actually? What are this, and this? So let me show you. So the output provided is actually a compressed sparse row format, which is the memory of, okay, this is just, you can just say that this is a sparse matrices. Okay. Each row represents a document. Document means one sentence we are talking about. Okay. And here we are talking about one sentence. It could be a paragraph when you're dealing with a larger data. It could be a paragraph. It could be a whole, uh, essay for that matter. Okay. Each row represents a document and each column represents a unique word in the vocabulary. The value represents the count of each word in the corresponding document. So let's say this is, we are talking about this 50 and 1. So each line I, J, and K indicates ith document. Okay. Ith document and jth word. So you can see, okay, this is, so far we are dividing the data into now zero point 0.4. Okay, so let me see how many are there. 336, 39, 12, 12 for 16. So right now it is saying, okay, 0, 13, 1 means what? Zeroth document and 13th word. And the vocabulary has a count of K. So when I'm saying 0, 8, so 0 in zeroth document, the eighth word has vocabulary 1. Sorry, the count 1. Okay. All are those unique words only, we can see only 1. The second document is, second document, the word represented by index 11, the vocabulary appears once. So that is what it is. It is just representing the document number, the sentence number, actually, which word we are talking about, and how many times that word has occurred. Okay. Now we are doing what? We are training the, now here we are going to train with this dot fit method. Now we have, because of the, count vectorizer, you can say I'm using not xtrain but xtr here. Because of this count vectorizer, I have categorized everything that I had into this format. Okay. So now I'm going to use, now naive Bayes here is nothing but the object of this multinomial MB class. This is the classifier that is actually used to train. Right. So what are we going to do actually in this? Is because of this fit method now, I'm going to train this X, whatever I've got here, and I've already have this white ring. So why do I have white ring? Because that is the label, right? Because I'm going to train this XTR and I'm going to associate white train label, whatever we have in the data. White train, whatever the label, we have this white train. Let me show you this, whatever these labels we have, those are the white trains. Okay, nothing else. So when I'm giving him this, I love to eat pizza, it will break it down. Okay, and then it will associate it with white train. Okay, because of this occurrence of words. This is actually the multinomial naive Bayes. This is the classifier. And here we are actually training. So we are actually computing the prior probabilities, then the conditional probabilities, and then we are going to predict. So this is where we are training, and this is where we are going to predict. So you need not, get into this, the depth of it, but you know that because it's a little complex, not as easy as KNN. So we know that we are training with fit and we are predicting with this predict method. Okay, if you want, you can go through it. So now make prediction on test data. So predictions is equal to naive Bayes dot predict XTS. Now what is this XTS? Again, we're taking that whole converted data, what we took here, this XTS. Because of this, because we have transformed it through because of the vectorized. Okay, now I'm printing X test, and let me print also this. Right, this is going to display what it is because it's in Google. Now it is saying I love to eat pizza. Pets, pets, pets. Again wrong. I have a cat named Fluffy. Now that's pets. So what is my accuracy actually? 28% is my accuracy. Reason for that is we don't have enough data to train. The more we train the data, the more accurate it will. So right now we have very less data and it is being trained and it is predicting based on that. When we have a good amount of data, then we'll actually be able to train and get a accurate output. Not 100% accurate, but at least 80%, 90% or something. So here I've just taken, okay, what if I give something? What if I give something, some word to this model? Will it be able to predict, right? So let's see. So fortunately, because of this cat is already being classified as pets. So when he is talking about cat, it is actually classifying it as a pets. So that it is correct. So let's say if I'm writing books, so it is classifying that as books as hobby. Okay. Again, it is not classifying this traveling to pets. Now that is wrong. It didn't understand what traveling was. Okay. It didn't have uh, proper training data. So that is okay. So that will conclude our NAT test. Any confusion or anything you want to ask, you can ask now, or we'll move to the next thing. I think we still have time, so we can move to the last one. That is experiment 9 of yours, which is finite words classification using backpropagation algorithm. All right, I'll take that. There's no other confusion or questions, so we'll move to this key forgetting the name. Yeah, finite words classification system. Okay, so the neural network we are going to use in this is feed forward a neural network. It's a basic feed forward neural network, and which has one hidden layer, one input layer, and one output. Okay. It is not actually the same. I'm just giving an example. Okay. So let's get into this. So first of all, as we know, we are importing NumPy as NP, because any array or any array operations we are going to conduct, because we are doing it, we are using NumPy. It's easier. So I actually got this much data. This I've added from my side. This whole thing I've added from my side. So cat, dog, apple, banana, car, bike, chair, table, board. You're seeing this, and you might be wondering, what is this then? The binary equivalent to cat is not this. So why we are actually using this? You know, why we are actually using this binary, and we are associating with cat. So the thing is, yes, it is not a binary equivalent of you know cat, but the thing is, we are making a custom binary. We are making a custom binary by via binary encoding. Okay, so these are the custom binary equivalents. Now we have a training data, and now we have a labels, of course. So what we are going to do, we are going to get something in the training data, and what are these labels? They are nothing but, okay, cat is an animal, right? Whenever I'm talking about this, it should give me, okay, this is an animal, and this apple is a fruit. So whenever I give this apple as an input, it should get me, okay, this is actually a fruit. So in this, here I'm giving input layer as one apple. So input layer takes that, process that, and in output levels, after output, it should give me that it is an apple. So why all this for, no, just a small thing? Because again, computer doesn't know anything. So it breaks it down into 8-bit system and analyzes every single letter. How is this associated with the label? Okay, so let's get into that. So we define the training data, which consists of words as binary feature vectors. Oh, that is just nothing. So let's get into this. What is this input size, hidden size, and output size? This means in this input layer, there are 8 elements. In this hidden layer, there are 5 elements. Like you can see 3 here, right? So because of what I have written, we will have 5 elements in the hidden layer. And the output layer will have 3 because I have written 3 here. These are the most important part of project, because this weights and biases will actually decide what would be your output. So through the all the iterations, we are going to you know get this weights and biases correct, and we are going to compare that with actual label. So till we don't you know till we don't get it right, we are going to you know do the iteration again and again and again. That is what back propagation is. Okay. So here we are actually using this weights and biases, weights 2 and biases. So as I said, that these values will be updated during training to make accurate predictions. These weights and biases will be changed again and again so that accurate prediction could be done. Now, learning rate is 0.1. That means every time there will be a correction of 0.1. I can increase that or decrease that based on my belief. So now I have taken this number of iterations as 10,000. That means what? It will learn for 10,000 iterations, and it will give me an output. Okay, finally it will give me a machine. Finally, it will give me a final values of weights and biases. So it cannot go indefinitely. Okay, So we'll have to stop somewhere. As I said that we are going to correct these weights and biases up to a certain point that it should accurate. But we cannot not write infinite loop, because in machine learning will never get, based on a very large output, will never get 100% accuracy. So keeping that in mind, there's always 97%, 98% accuracy, but 100% it's not even desired. Okay. So that is why I've taken number of iterations as 10,000. So 10,000 times is going to backpropagate, and 10,000 times is going to correct the values of weights and biases. These are the sigmoid functions. These are the activation functions. So these activation functions actually, is convert the weighted sum of inputs into the value between 0 and 1. So e the power x divided by 1 plus e the power x, that is the sigmoid function, you know that. So this we use this weighted inputs and everything, weighted sum of inputs, and we convert that into activation function. We use that activation function. This sigmoid function actually makes a sine wave. Sorry, not a sine wave, a curved wave, a curved graph you will see. So what is this now? We have defined this. This is the sigmoid function. What is this now? For iteration range, num iteration. So this will run 10,000 times. So this is the loop where our neural network is being trained. Trained means what? The weights are and biases are being changed. So let us get into that. So why we have taken actually two weights and biases, and we do with one? Okay, so let me tell you what. So weights and biases, when we go from input layer to hidden layer, then we use weight one and bias one. When we go from hidden layer to output layer, then we use weight two and bias two. Okay. So as it's saying forward pass, now we are forwarding, we are going forward. Okay. So back propagation is not being displayed here. So, but there is a back propagation in this our algorithm. So let me see if I can find diagram for that. Okay. We're not even getting a clear picture of what we want. Just consider that this comes back. Okay. Train the weights and everything. All right. So in forward pass, what we'll do, we're going to calculate the input of hidden layer, the training data and weights one. Okay. So we have a training data as input. Now that training data, why am I saying 8? Because I have broke it down in 8 bits. That is why I've taken 8. Okay. Now, so when we're talking about the neural network and what is a neuron, that one bit is a neuron. That one bit, that one bit that I have taken, this one is a neuron. This one thing is a neuron, and that is one bit of a single, you can say, a word. So this is the training data, and this is weights one plus biases one. So this is where we are creating hidden layer input. Now hidden layer output is being calculated using this sigmoid function. And what I said, this is the sigmoid function. Okay. So it will, as I told you, this the formula for sigmoid function. Okay, all right. So it is doing this 1 plus e to the power x in power minus x. Sorry, is what it is doing. So now I have a hidden layer output. So this output, after coming from hidden layer, This is what I'm getting, and that is ready for the output layer. So now for output layer input, what would be the input for output layer? That would be the hidden layer output. So for hidden layer, the output was the training data. Okay, if there are two, yeah, leave out that multiple output hidden layers. So when we're talking about output layer input, whatever hidden layer output, whatever it gives, that would be the output layer in here. Whatever it is giving here, WK1, so it is going from here to here. It is generating an output and it is giving to output layer as the input. Now, how are we going to create output layer output? Same, sigmoid function. Okay, we'll come to the sigmoid derivative too. All right. So now this is the backward pass, means the back propagation. The output error labels minus output layer out. Okay, so we will getting an output from output layer and we have labels. Okay, now since we have taken our training data and we are creating an output layer, sorry, we have taken the training data and it is, and we have the labels right here. Then we are matching the output to the label, whether it is equal to the label or not. Now, if we find error, that will be the finite value of error. Now, out when we are going to create an output delta, output error into sigmoid derivative. Because of this, now have something. Okay, I know that there is some error. Same way, it is going again. So now, hidden layer is accepting a kind of input from the output layer, back propagating. Okay, it's not the exact input, you can say. So it is taking, and now it is going to create an hidden error. Now output delta dot weights 2. Now we are using, we are, because this is what, this is an array, right? Okay, you can say a matrix. We are going to transpose that matrix, and this is the whole thing, the mathematical thing. So it will take a lot of time actually to explain. So we are creating a hidden error. After that, we are going to create a hidden delta. Okay. Now, are we going to use this hidden delta and output delta? Okay. First of all, we are going to create weights to n. So as I said, that we are going to actually change the weights, and the weights will decide the output. That is what it is doing, right? The weights and the biases are going to decide the output. So weights 2 plus equal to hidden layer output dot e dot output delta into learning rate. So the correction we are doing it with the scale of 0.1. So we are just whatever output delta we are getting, we're multiplying it by 0.1. So there is no, because that is why we are writing plus equal to. We are adding that to the weight. Now biases 2. Same we are going to use that output delta as 6 is equal to 0 means it will go through the row into learning rate. Same. And that is how we are going to create weights 1 and biases 1. So we know that weights 2 here, weight 2 here is used for from hidden layer input to output layer. So when I take input from output from hidden layer and treat it as an input, treat it as an input for the output layer, we use this W2, that is weight 2. That is what we are actually, and that is what we are actually correcting here, and we are using hidden layer output for that. Okay, we're using that. Sorry, we are using output delta for that because it is back propagating. So we are using output delta that we are getting here. So this is where we are getting the output delta. Whatever there is a, whenever there is a lack of accuracy or there is an error, we are creating an output delta. And then we are back propagating it. And we're using this actually create weights too. I mean, sorry, increase the weight too and the biases. Now, since we have this hidden delta 2, which we have created, that is used for correcting this W1, that is weight 1 and biases 1. So in this, so this is where we are actually creating, actually correcting weights and biases in every single iteration. Okay. Now, more the iterations, more efficient your algorithm will be. So that we have run, I guess. Yeah. So now the neural network has been trained. Now this is the test data. The weights and biases that you're seeing here are the final values of weights 1 and biases 1. Okay. That is what we are going to use to make this predicted labels. So now what is this, what are these predicted labels? Let's see. So right now, this doesn't mean anything, right? So we are going to check its accuracy. So these are the test labels, actual labels. So labels are in the column, so that is why we are taking x is equal to 1. Okay. So right now we are getting 40% accuracy. We increase the number of iterations and run on. Now, because I've doubled the number of iterations, now you can see the accuracy is 80%. Before, it was 40% in 10,000 iterations. So, as I said, the more you train the data, the more iterations you will have, the better your algo will perform. So, let's say I have given only 1,000 iterations. Sixty percent. Mhm. So every time it is giving me a different value because I have not, because every time we are creating a different random numbers, right? Every time we are creating a different random numbers. That is why every time we are getting a different output. Right now, this will give me a different one. Now we are getting 80 again. So now what is this 0, 2, 1, 0, 0? So let's say this is the zeros category. So cat belongs to zeroth category. So actual label. This star belongs to this 2th category. Okay, second category. This apple belongs to fruit. Apple belongs to, yes, this apple belongs to again first category. So now it's predicting 4 of them accurately and one of them it is not accurate about it. So I'll go 80% accuracy. Okay. So also we have a less amount of data here to train. That is also the reason of fluctuating performance. Okay. So this algorithm will help you to train the machine on the language, basically. Okay, categorize actually. Okay. Categorize. Okay, how do you know that a particular thing is belongs to which category? So when a child sees a cat or an animal, how does he know? Because he has been trained. Okay, again and again, he makes error. Where again and again, okay, this is a cat. This is an apple. Okay, how this cat is a animal. This apple is a fruit. So that is how we are again and again we are going to uh, run this neural network, and we are going to correct the weights and biases again and again to train the data. So if you have good amount of data, you will be able to train it accurately, almost accurately. You will get at least 90% or something like accuracy. Okay. If there are any questions, I guess there's no one here. So that will conclude um, all three labs. That was today's agenda. So thank you very much. I'm ending this meeting because